All right, well, I think we should get started and welcome everyone to the Tuesday seminar. Today we have two speakers. We get two for the price of one. And the first one is going to be Kantorn Thammakul, who's been working on the development of a fuel cell lab. He's made a lot of progress. And this is not his first presentation, but you will see how much progress he's made in developing some experimental facilities for the purpose of, he will explain. Go ahead.
Yes. Hello everyone. My name is Kantorn Thammakul, a student under Professor Risoni and Dr. Manfredi guidance. We are working on something about fuel cells, and today I will be presenting something about how we develop a fuel cell test lab at PAR. The presentation will be pretty much similar to last year that I have talked, but I just add some progress into this presentation. And I just want to show you some cool stuff that we've been doing. Spoiler alert, the lab is not running yet. It's not operational, but we are like few sensors away to be functioning. So yes. So the outline will be like this. First, I'm going to talk a bit about introduction, what and why for fuel cell. And for our interesting application like heavy duty vehicles, we are going to talk about the operating hours requirements of the fuel cell application in heavy duty vehicles. And I will talk briefly about testing methods and what are used as the health indicators for the state of health of fuel cell. And I will talk about brief story of the fuel cell degradation and what are we going to do for our research. And I will jump into the setting up the lab. I will talk about the components, what we have, what we need now, and what I'm expecting from what we have been doing. First, what are the fuel cells? Just to refresh, some of you may know, some of you may fuel cells are. Fuel cell is pretty much the energy conversion device. To me, it's more like engine more than battery, because battery is kind of energy storage device. For this fuel cell, it converts the chemical energy, which is hydrogen and oxygen from air, into the electricity. By the way, fuel cell itself can use various kind of fuel cell. Fuel cell itself can use various kind of fuel, depending on the types of the membrane that they are used. Fuel cell has no combustion. It only has electrochemical reaction. It has high efficiency and clean energy. And mostly they are categorized by the type of the membrane. And what are we focusing on is the PEM fuel cell, which is the polymer membrane type, because PEMs are widely used in automotive application. So talking about the automotive application here, we are thinking something like the heavy duty vehicles. So we know that this kind of heavy duty vehicles, such as trucks, they have like a fixed route that they have to go. They have to carry the loads, they have to carry the passengers, and they have to make trips, like many trips per day. And we know that these kind of vehicles usually comes with diesel engine powertrain, which of course produce emission. To make them more cleaner, the first thing that come on top of their mind is to make this vehicle be more like a battery electric vehicles. But to do so, they have faced many challenges with putting a battery into the heavy duty application, such as the large battery size, which will increase the vehicle weight. Increasing vehicle weight will increase the load requirements, and they take long charging time or high power charging infrastructure. But fuel cell can offer the middle ground for that. This fuel cell can have less weight. Fuel cell can offer fast refilling, like 10 to 15 minutes for this kind of vehicles. And of course, fuel cell can produce zero tailpipe emission. They produce just warm air and water. And as you may know, fuel cell is not attractive for passenger vehicles because fuel cell system itself, it has high cost to be adopted into the vehicles, especially for passenger vehicles. And also like almost nobody wants to invest the hydrogen infrastructure in the state to build a gas station, like fuel cell gas station. And also the other thing is that the battery electric vehicles already dominates the passenger vehicle. With that, fuel cell is still like attractive for heavy duty vehicles. And for the heavy duty vehicles, as we have mentioned, it has to be operating in such a long time. And many organizations has set up some target of the operating hours requirements for fuel cell in heavy duty vehicles like bus and trucks. These organizations are looking for something like tens of thousands hours of operation for fuel cell in heavy duty application. And this is one of the main reasons why we are interested in investigation of fuel cell remaining useful life, because if we can predict the remaining useful life, that means we will have some knowledge to develop fuel cell to reach this target. And these people also come up with some different testing methods. There are several test methods that they have been using, such as long-term durability test. They might just like put the cell into the test at the constant load and hope that the cell will degrade through the time. And they may have some kind of AST, which is the accelerated stress test, which they can stress the cell with the harsh operating condition like high temperature, low humidity, and hope the fuel cell will degrade with those conditions. And they may put the cell through the driving cycle just like what they have done on the battery. And they hope that the driving cycle can mimic the can contribute the degradation according to the real life operating condition. However, through these methods, they still don't have like universal official test protocols, which also one thing that we have to consider about when we do test, especially when we try to say that degradation is true happens like in real life. And for example, there are some organization body called named Million Mile Fuel Cell Trucks or MGFCT. They have proposed the AST protocols to test the fuel cell to see the degradation on the membrane and the catalyst. The test protocol is more like vary the load profile like this and stress the cell with the different temperature and humidity. Just to give you some idea how people have been doing this test. And with those tests, what are we looking for from the test results? We need to look for something that can be used to describe the state of health of fuel cell. And people have talked about several things here. The first one is the voltage and power, because the voltage of fuel cell decreases over time as the cell are used. So the healthy cell, of course, can maintain the higher voltage under the same load requirements. And as the cell age, even though we give the same amount of the reactant or fuel into the fuel cell, they cannot provide the same level of voltage with this age. And of course, the voltage power is something that is that reflects the overall system performance. Another health indicator that people are talking about is the impedance system. This thing can be studied or investigated in the areas which is the electrochemical impedance spectroscopy. And let's say that the impedance will be treated as resistance of the whole system. That means when the cell degrades, we are expecting an increase in the impedance. And also for voltage, power, and EAS, these two are kind of non-invasive tests or non-invasive characterization. So that means we don't have to break the cell. We can stop operating and do the characterization anytime we want. But we also have the invasive test, which is the structural and morphological analysis techniques. But the thing is that this is quite destructive because we have to take the membrane out. We have to cut and prepare the sample and put the membrane to the microscopy such as SEM, TEM, and XRD to study the real physical degradation, just as shown in the figure here. So talking about the degradation, many researchers have described the kind of degradation of the fuel cell as the mechanical degradation, thermal degradation, and chemical degradation. So let's say they have like three main degradation mechanisms. And as we are focusing on the fuel cell, automotive fuel cell, so that means we will have some kind of operating condition that we will face through the day or through the fuel cell life, such as the open circuit voltage or idling, startup and shutdown, and dynamic load. These operating conditions contribute to different kind of degradation mechanism. But the thing that I want to point out here is that there are two kind of degradation on the component level that really affect the fuel cell performance. The first one is membrane degradation, which is grouped as the blue group here in the figure. And the other one is the catalyst degradation, which the catalyst is on the electrode. So they will be grouped as the orange group here in the blue. So after all the previous slides, what are we going to do? So we are going to investigate a fuel cell degradation, and we hope that we can make some fuel cell degradation model and develop some prognostic system to do the prediction of the remaining useful life of the fuel cell. So let's say we have the cell at the beginning of life here. We are going to put the cell through the aging test, which it might be a mix of the accelerated stress test and the driving cycles. And after hours of operation, we are going to pause it and do the diagnosis, which is the characterization test, such as the polarization curve or EIS to study the characteristic curve of fuel cell and the impedance of the fuel cell. And we are going to keep doing this over and over again to up to like certain hours or up to the point where we decide that this is the end of life fuels. And to do that, we need the lab. That's why we are trying to build a lab here. So starting from the stack itself, yep, many people or some of you might ask, why don't we just buy the test rig, like the test rig that is already available in the market? The first one is that the test capability of the rig, because to go to higher test capacity, let's say like for 1 kilowatts or more than 1 kilowatts, the test rig would become quite expensive. That's one thing. And the other thing is that the test rig available in the market usually are made for the size of the cell that comes, which is like 5 centimeters square or 50 centimeters square wide. Our cell or our stack has the size that is similar to the real fuel cell stack that is used in the fuel cell vehicles, which is about 250 centimeters square here. So that is one point why we can buy the whole test rig. Yeah. So for our case, we have a stack with this size, and this stack can stack the cell up to many cells, but we aim for just like 1 kilowatts of this 6-cell stack here. And this is the liquid cool stack. As you can see, they have like one channel just run through the stack to keep the temperature. And also we have to calculate it. We have to calculate the reactant consumption to buy the mass flow controllers. Unfortunately, there is no mass flow controller that we work to cover all the range of 1 cell and 6-cell of flow rate here. So we decided to pick just the mass flow controller that can use just one system. Well, this is the level of mass flow rate that we have calculated. This is not zero, but it is very small. Usually, hydrogen consumes very, very small amount of. Usually, hydrogen is consumed at a very small rate comparing to the air. So that's why this is nearly zero, but it's not zero. And this is one component that give us pain through the second half of 2025, the humidifiers. So there are many types of humidifiers to be able to use with our system, but since we have to customize and custom make by ourselves, we choose to go with the gas bubbling humidifier here. So to do that, we have to, of course, calculate the amount of water that we need to stay operating without us has to come to the lab and refill the water frequently. So yeah, we calculate and choose the size and buy the sensor, which is this relative humidity sensor, and then the humidifiers by ourselves. And this humidifier gave us a lot of pain because at the first version of the design here, it has so much of condensation problem. So we have to modify the tank again by putting the immersive heater just to keep the tank warm and wrap the tank with the strip heaters just to maintain the temperature and also insulate it. And as of now, as of this design, we can improve the system to be around 80% around hours of operation. And also we have to control the pressure of the system. So we have the pressure pilot control, which will be used as the back pressure regulators. And also we will measure the temperature at the multiple location throughout the system. At least these are 6 points that is necessary to so we have programmable DC electronic control load, which this one is capable up to like 1.5 kilovolt with the maximum voltage of 60 volt and maximum current of 600 amps. The thing is that we are looking for something like 375 amps and up and 1 to 6 volts because fuel cell does not generate high voltage, but it can generate high current. So I have to write everything from the scratch to make the lab view data monitoring and logging system. And this is what we have to do. And what are we expecting? We expect that this setup can provide control environment to study key factor that affects the user performance and lifespan. We hope that we can identify the degradation mechanism. We want to evaluate operational conditions that contribute to the performance loss. We want to develop the diagnostic method. We want to optimize mitigation strategy. And ultimately, we need reliable data. And speaking of the data, last year, around October, November, we just filed some public available data from IEEE Creation Challenge 2014. We know that this data is like 11 and up to like 12 years old already. But yes, we use this data as a pre-study of what we think we want to do. This test was done on a stack of 5 cells with 100 centimeters per size at a constant current of 70 amps for like 1,000 hours. The data comes with the time series of voltage, current, and many other profiles such as the temperature, relative humidity, pressure, and all the environment of that test. And also they have the characterization data, which is the polarization curve and EIS impedance here. So what we have tried is that we use the data from the polarization curve here and match them with a simple fuel cell degradation model. And we look into the degradation indicator, which in this case is the resistance R and the exchange current density I0 here. So we fit the data with just only simple non-linearly square fit to get the value of R and I0 at each hours here. And we say the evolution trend is that R increased with time, which is what we are expecting. And the I0 here decreased with time here. And then we assume that these two parameters has the linear relationship. So we just build R as a function of time and I0 as a function of time and plug it back to the model. And this is what we got. So this is the plot between the voltage and time. So the blue one is the real data and the orange one is the model from fitting two parameters. So that is pretty much what we have done briefly. lately, and we hope that the fighting from this work will help enhance fuel cell durability and accelerate the adoption of hydrogen-based energy solution, especially for heavy-duty vehicles. Thank you very much.
Thank you. Questions?
I must say that's interesting to see maybe again fuel cell research is back. I don't know. I mean, in future, in past, I believe it kind of stopped it.
We stopped, yeah, we did fuel cell research when Jan was here. He was at.
Yeah, because then
We never quite did something like this related specifically to the aging and degradation of fuel cells. We did more on the topic of system integration and system modeling and control. But this is what we understand could be of interest to the community of people, mostly in the commercial vehicle sector, who think that maybe there is some potential application for fuel cells. Kantorn said that in the beginning. Unlikely that you'll see really a big passenger car adoption, but for commercial vehicles, there are some avenues. But I have a question, Kantorn. You showed that initial preliminary analysis based on that public data, right? But that data is not really sufficiently interesting for the purpose of understanding degradation because it's constant load. For an automotive fuel cell, there would be load fluctuation. So just say a couple of words about what you're doing to improve.
Yeah, for our test, as Professor recently said, this data comes with just constant current, and what we plan to do is for our test is that for our test we have to consider about how are we going to test the cell to get the real degradation that could explain the degradation that we may face in real life when we use the fuel cell vehicles. So to me, what I'm thinking now is that I will adapt a simple drive cycle plus some stress test with the AST and use it as the way to
Combine those two ideas.
combine those two.
And we'll probably borrow some ideas from some of the standard testing that has been done on lithium batteries, where you have cycles that imitate real driving, right? Yes. So, thank you. Any questions from the people online? So if there are no questions from the online crowd, let's thank Kantorn again. Thank you. And let's move on to a different topic. Pooja has been working with the EcoCard team for the past few years, and she has been responsible for leading the connected and automated vehicle systems component of the team. And some of the work done in on the EcoCar project provided motivation for her dissertation topic, which has to do with the subject of automated parking, and she will explain to us what happened. There you go.
So good evening, everyone. So I will be presenting on the topic of human-inspired predictive perception and trajectory planning for automated parking. I would like to give a brief overview of the work that I've done until now and what are the topics that I'm proposing for my dissertation. So Parking maneuvers itself are one of the challenging tasks in automated driving, as it requires the vehicle to navigate through tightly constrained environments. And the environment itself is very complex because of the presence of static and dynamic obstacles. So if there can be pedestrians or vehicles which are parked or going about in the parking lots. So based on the degree of autonomy, the feature can be identified as a park assist feature or a valet parking feature. The park assist feature is an SAE level 3 feature where the driver has to take control whenever required. And the valet parking feature is an SAE level 4 feature where the driver would get off the car at a particular location and the vehicle needs to maneuver autonomously and find a parking spot and park itself. The feature has to be designed for a number of scenarios. As parking spaces are not standardized, they can be indoor or outdoor spaces. And when it comes to indoor or even semi-structured spaces, availability of GPS becomes challenging. So furthermore, the feature can be divided into 3 main modules: perception and parking spot identification, the trajectory planning, and the delivery following. Parking spot identification, I think, is a key step because it determines the success or the failure of the vehicle. Many techniques in the literature talk about addition of infrastructure sensors, V2X, or parking management systems, which basically provide the details of an available parking spot and its location. And like I said before, dependency on GPS or offline maps or predefined maps limit the scope of the feature. So this led us to our high-level problem statement where we wanted to develop an end-to-end SAE level 3 park assist feature. The idea was to develop a thoroughly tested perception and trajectory planning framework using sensors that are mounted only on the vehicles. And as it's a park assist feature where the driver is again going to be in the car, we wanted to develop a more human-like feature where we minimize time so that it is comparable with average parking time for a driver. We did a thorough literature review and identified what the state-of-the-art techniques are and what gaps there exist in current literature. This dissertation will be addressing 3 of these gaps. Firstly, the techniques proposed require the vehicle to partially or fully pass the parking spot to be able to determine its occupancy and say that, okay, this is the valid spot. And this leads to increased time for the final selection of the spot. Secondly, backing into a parking spot is a more commonly adopted strategy. Straightforward and pulling maneuvers are relatively underdeveloped. Thirdly, real-world constraints and uncertainties lead to tracking errors. And when the controller is not capable of correcting that error, planning a new trajectory becomes essential. So, and replanning strategies are, again, relatively less explored in the literature. A major part of this research is conducted as a part of the EcoCar EV Challenge, which is a 4-year-long student competition sponsored by CM, MathWorks, and ANL. As a part of the competition, we received the 2023 Cadillac Lyric, which offers an automated park assist feature for parallel and perpendicular parking configuration. The stock feature came with 12 ultrasonic sensors as its sensor stack. We did multiple tests with the stock vehicle for both these configurations and with and without the presence of an adjacent vehicle. And these were some of our key observations. As it uses ultrasonic sensors, it requires an adjacent vehicle or a curb to identify a free space. Maximum reference objects led to better performance. The test was successful when the adjacent cars were centered in the spots, and when the cars were not centered or it was any non-ideal placement, the test failed. This is mainly because ultrasonics prioritize maintaining maximum distance from the obstacles to avoid collision. And spot identification was sensitive to vehicle speed and distance. So if we were going further away from the spots or going too fast, it failed to detect the spots. After baseline testing was done, the team redesigned the vehicle And now the available sensor set includes GM stock sensors and team-added sensors. The GM stock sensors include the front camera module, a long-range radar, 5 short-range radars, and 12 ultrasonic sensors. And the team-added sensors include a CODA NK6 for V2X communication and 4 LiDARs. Here we have selected LiDARs as our sensor stack for implementation of the feature. The image on the right here shows the hardware setup. We've added two controllers, the CAF supervisory controller and the propulsion supervisory controller. The sensors are interfaced with the CAF supervisory controller, which in turn sends out longitudinal torque requests to the propulsion supervisory controller. Now this controller is responsible for distributing the torque to the motors, as well as determining whether the request that we are sending is going to be honored or not based on the vehicle state. The deceleration request, transmission states, and steering torque and angle requests are sent to the corresponding GM modules. And the HMI notifications are sent to the team-added display and the GM display. The first step was to define the functional and safety requirements for the feature. Some of these requirements are governed by the requirements that were imposed to us by the competition. So these set of requirements decide the intended functionality of the feature and also adds constraints to the development process. As I said before, we have chosen the LiDARs as our sensor stack. So we have 4 LiDARs mounted around the vehicle to give us 360-degree coverage. All these LiDARs are first calibrated with respect to the front LiDAR. Then the ground points and the non-ground points are analyzed separately. The ground points are parking line information is extracted out of the ground points. And for the non-ground points, the vehicles and any obstacles would be detected. So for that, a density-based clustering method was used and an occupancy grid was created to firstly discretize the environment space and to create a go-no-go zone around the vehicle. To give a brief overview of the system that we are proposing, once the feature is enabled, the first step is going to be LiDAR processing to detect the obstacles. Here, the ground points would be analyzed to extract parking line information. And based on the free space that is identified, parking spot candidates would be generated. A Kalman-based tracking method would then be implemented to track each of these candidates. Here, 3 types of uncertainties are considered. Sensor noise, detection accuracy, and inaccuracies due to limited sensor visibility. So all of these 3 uncertainties combined, we would assign a dynamic confidence score to each of these candidates. And it would be updated in real time as and when we get more and more sensor information. So for example, here in this image, the left parking spot would have a higher probability of a higher confidence value than the right parking spot. A final parking spot would then be selected based on this value, and when it reaches over a certain threshold value, the spot would be selected, and the locations and dimensions would be sent to the trajectory planning module. The first step here would be to localize the vehicle with respect to the obstacles and the spot to determine a target vehicle course. Now, based on the relative position of the vehicle with respect to the spot, an appropriate parking strategy would be selected. So what do I mean by an appropriate parking strategy is that are we going to do a forward maneuver and pull into a spot, or are we going to back into a spot? Once a parking strategy is selected, waypoints would be generated and a trajectory would be planned, which would be sent to the controller. Here, the controller would continuously monitor the tracking error and assess the situation for any possible collisions. So if the error is small and the controller is capable of correcting that error, the process would continue. If there is a collision that is predicted, the current process would be stopped and a new trajectory would be planned again from the current position to park in the spot properly. Now, as this entire system is initialized or triggered on a certain on a certain probability, it is possible that as we move as the vehicle moves forward and we get more information, there is say for example an e-bike or a phone or a shopping cart which basically says that now this we cannot park in this spot. So in that case, it would mean that the selected spot would become invalid, and the current process would again be stopped, and a new trajectory would be planned from the current position to start the search phase again. This proposed approach would then be experimentally validated using a V-model approach. The primary track is to first test in simulations and then move to hardware testing and on-vehicle testing. Here, the risk that I wanted to highlight is the availability of a working vehicle. In case the vehicle does not remain functional at any point of time, we would move to a simulation-based approach where bill verification would not be possible. Everything up until component simulations can still be done. In this case, a high-fidelity 2DOF plant model might be required for setting up a hill testing setup. As a precaution, right now we are collecting data so that we have enough information to continue with the research and the outcome would not be deviated. In worst case, we still have access to the vehicle and sensors which can be powered externally, and more data can still be collected. The final outcomes for this dissertation would be a parking spot identification strategy, which is capable of taking proactive decisions to select a final parking spot. Secondly, an optimized parking planner, which selects between a back-in or a pull-in maneuver to minimize time for execution. And a collision risk-based replanning module that plans a new trajectory if the spot becomes invalid or if there is a collision predicted. So these would be the final outcomes.
Questions from either the local audience or the remote audience? Let's see. Okay, if there are no immediate questions, I'll ask you one. What was the hardest question you were asked during your candidacy exam?
I would say the hardest question that I was asked is how would I estimate how would I come up with that confidence score based on different uncertainties that we have. I spoke about 3 uncertainties, but we also we discussed about more uncertainties that are possible. So if, for example, there would be hash lines. So because we are just using LiDARs and not using any vision sensors, how would we detect those kind of lines? So right now the plan is to see if it is possible using LiDARs. That is something that has been done in other research papers. So we at first we would be trying that, but then we want to come up with a way to kind of integrate all these uncertainties and come up with like one confidence score for each of these candidates. So estimating that.
But would you consider using vision information with LiDAR information? There are some things that cameras naturally do very well.
Yes, for sure. That would definitely give a rich data set if we do use camera and LiDAR information. And again, like many techniques have in the literature, whatever I've read, is to combine a lot of like ranging and vision sensor because it kind of complements each sensor. So it definitely would give a richer data set than using just LiDARs.
And the process of identifying and mapping a trajectory once you have determined that you have an available parking spot, now you have to imagine the trajectory that the vehicle will follow to enter into that parking spot. What are the approaches that you think you will use? More than one. What are options that you
So as we have, as this entire system would be triggered early on, we might not have the final location of where it would be parked, but we would have an intermediate target spot where we want to go, and then as more information becomes available, the next part would be planned. To start with, I wanted to go with very simple with some geometric approaches using basic arcs and segments kind of methods. But now this becomes a discontinuous method. There are various other continuous methods that we could explore, which would give a more smooth trajectory.
And based on your experience with doing some early testing with the GM system, which is based on ultrasonic sensing, right? How smooth was that? What are the things that struck you as a subject of improvement?
So firstly, with detecting the spot itself, it was less reliable, because like I said, if we were going faster or even slightly further away from the spot, it completely failed to detect the spot.
And the first time I tried, I couldn't do it.
The system was
It would
not
not work.
reliable at all. So that is something where there's definitely scope for improvement. Secondly, because it uses ultrasonics, it is more of a collision avoidance based planning system. So it would do on an average like 4 to 5 back and forth maneuvers to kind of get into an ideal spot to.
It does it by successive approximation,
Yes.
right?
Less number of like back and forth movements, and a smoother trajectory is another area where there's definitely scope for improvement. And thirdly, time, because it does all these back and forth maneuvers, it takes on an average 1.5 minutes for parking in a very simple part. So if the driver is in the car, it's going to be frustrating, and the driver is not going to use that feature at all in these cases. So it should be definitely faster, comparable to what we're doing.
Right. So it's a feature that unless for whatever reason you are not a confident driver or you have some disability or something where you can really use that assistance, it's not something that you would choose to use. It's a lot faster to just go park. Okay. Any more questions? Thank you, Pooja. Well done. Thank you, both speakers, and for those who attended, thank you for coming.